Okay, today we start a new chapter. It's chapter 5. Arkadaşlar sessiz olur musunuz? So this chapter deals with the laws of motion. And in fact, we are entering another subject in physics. So far, the first first three chapters, were dealing about the kinematics of the motion, where in kinematics, we don't need to know the cause of motion. We have objects are moving, and we haven't considered the forces behind this motion. But starting from this chapter, we will deal with the causes of motion. We have objects are moving, but what the cause of their motion? Okay. So we will see a new physical concept is needed for that. One is the force. Okay, I will introduce what the force is, and there are of course different types of forces, and also the mass of the objects are important. Okay. The action of the forces on objects and the masses are the concern of the laws of motion. Okay. So, as you know from your daily experience, that the force can be defined as push or pull. Okay. If you push an object, then you apply a force on it. Biraz daha sessiz arkadaşlar. If you pull an object, then again, you apply a force on the object, okay? And as a result of this application of the force, the objects will start their motion, okay? The force is a vectorial quantity, so in addition to their magnitude, also direction are important. In which direction are you pulling the object or pushing? So we have to decompose the forces on the axis to analyze the motion on both axes. Again, with this chapter, we will analyze the motion of the objects in two dimensions, mainly x and y. That means you have to decompose your forces into x and y components. There are, as I said, different types of forces, and maybe you don't feel them in your daily life, but your existence, first of all, is a result of a force. Okay? Your motion on the surface of Earth is a result of a gravitational force. It's a field force acted on you by the Earth. Okay? And the particles in your body, the molecules, attach themselves by the help of electrical forces. Okay? Electrical force, electromagnetism, is another kind of force which is not like gravitational force, and it concerns about the charges that you will see in your next semester. We will analyze what the charges are and what the electrical forces. But at the end of the day, electrical force is a type of force. And it is one of the major cause of your existence. Okay? Your particles, your molecules in your body attach themselves to make your body as a whole with the help of electrical forces. Okay? Atoms. You know, atoms consist of nucleus in the nuclei and electrons orbiting around the nucleus. These electrons are attached to atoms as a result of a force, again, which we call electrical force. Okay? And this is not like a gravitational force between the astronomical objects, but it's another kind of force. Gravitational forces, the electrical forces, the forces inside the nuclei are all examples of field forces. Okay? There is nothing between the objects, but force. You don't see anything, any string or another spring, another mediating media that conveys this force onto other object, but they are the field forces. You don't see them, but you feel them. Okay. But on the other hand, you also have contact forces. These examples are the examples of contact forces. For contact forces to occur, the objects need to touch. Okay? They need a contact with each other. You either pull a spring or a string to convey the force of you onto another object, or a kick, or whatever. But if you analyze these contact forces microscopically, okay, this is a contact force, right? But what prevents my hand go into the table? In fact, it's a field force. It's an electrical force. It's an electrical force between the electrons and molecules in my hand and the molecules and electrons on the table. They do not go inside each other because the electrons repel themselves. Okay, so it's another thing that this is an example of field force, but we call these contact forces because we touch them. Anyway, this is not the concern for this course. Only it's for information. When we deal about the laws of motion, it appears that there are three different kinds of laws. Okay, the first law is found by Newton's, and it says an object moves with a velocity that is constant in magnitude and direction unless acted on by a non-zero net force. If you have an object moves with a constant velocity, okay, in space under the action of any force. Imagine that object moves in the outer space. There are any gravitational fields, nothing, any planet, any star. This object will continue its motion, its velocity with a constant velocity forever. It won't stop. Okay? But this is true only if there are no forces on the object. Okay? Or if there are forces but their sum is zero. Okay? If there are forces on the object but their sum of the forces as a vector is zero, this is also true. Object will move its state of motion forever. It won't change neither the direction nor its velocity. If the object stays at rest, if there is no motion, again, if there are no forces on the object, it will stay at rest forever. It won't move a little bit. So this is the first law of motion, and we call Newton's first law. Let's think about this question for you. We have a surface, a tabletop, you see here, and we see from the top, and there is a barrier, and there is a ball which moves touching to this barrier in this direction, and it comes, because of the barrier, the ball changes its velocity, right? Because it's changing the direction. It comes to the end of this barrier. Imagine there are no frictional forces between the ball and the surface. What happens after this endpoint? Does it go in this direction, completing the circle in A? Does it go in the direction of C, or does it continue its motion along this line? Who says A? No. Who says B? Who says C? There is no any gravity. You just see the ball from top, okay? The motion of the ball is constrained on the surface. Okay? Yer çekimi etkiler mi arkadaşlar? Sürtünme yok. Top yüzeyde dolaşıyor. Yer çekiminin bir etkisi yok. As long as the ball stays on the surface, and it will stay on the surface because there is a table, okay? There are no any forces acting on the lateral dimensions, on left, right, or top, down. No any force after this endpoint, right? Right at this point, what is the direction of the velocity of the motion? It's toward B, right? It's going in this direction. So it will continue its direction, its motion of the direction, because there are no forces on the lateral directions, neither up nor down. There are no forces, so it will continue its velocity with a straight line. Okay. So when we deal with the motion of the objects under some forces, of course, we have to take into account the mass of the object. If you apply, let's say, 10 newtons of force, by the way, the unit for the force is Newton, okay? 1 Newton is 1 kilogram meter per second square in terms of kilogram meter and second. If you apply 10 Newton to a 1 kilogram object and watch it motion, it will first of all speed up, right? It will increase speed for a while. And if you apply the same force to a 10 kilogram object, a larger object, will it move in the same fashion as in the previous object, which has less mass? 10 Newton'luk bir kuvveti 1 kilogramlık bir cisme uygularsanız, cismin hızlanmasıyla 10 kilogramlık bir cisme uygularsanız o cismin hızlanması aynı mıdır? So, obviously the motion of the objects also depends on their mass. Not only the application of the force, but it depends also on their mass. And we say, when we apply the force, we will see the object will change its velocity, right? It will increase for a while its velocity. That means if there is a change in the velocity, there is acceleration. So this value of the acceleration is, we call, proportional to the force, the applied force. If you apply twice the force to the same object, its acceleration will be twice. It is directly proportional. But if you increase the mass of the object, okay, you apply the same force, then in this case, the acceleration will decrease. So we say the acceleration and the mass of the object are inversely related to each other. For a larger mass, it is more difficult to move the object than less heavier masses. Okay. So as you know from the first lecture, the unit of mass is kilogram. It's one of the fundamental units of physics, and it's a scalar quantity. So, what was I talking about the motion of the objects under the application of force? In fact, I was talking about the second law of motion. So the second law says that the acceleration of objects are the total forces acting on the object divided by the mass of the object. As you see in here, if you have a larger force, the acceleration will be larger. If you have a larger mass, the acceleration will be less. Mass and acceleration are inversely related to each other, and this is the compact form of Newton's second law. The total forces on the object is equal to its mass times its acceleration. Okay. So you can also check the unit of the force from this equation by using the dimensional analysis, and you can easily say, since the unit of mass is kilogram, Let me write in here. And the unit of acceleration is meter per second square. This is the unit for mass, for the force, and it is shortly called Newton. 1 Newton is 1 kilogram times meter per centimeter square. So this is the definition of the unit of force. And this is the unit that we are going to use in the SI unit system. This is true in the SI unit system only, or MKS. Okay. So since the force and the accelerations are both vectors, we can analyze the motion then by decomposing these vectors into 3 different components, x, y, and z. But for the time being, most of the time, we will deal with the motion in 2 dimensions only. So that means all the forces acted on the object in the x directions, in the x direction only, will help you determine the x component of the acceleration, and all the forces acting on the y direction will help you determine the acceleration on the y direction. So in fact, the previous equation, this one, is in fact 2 equations, okay, for 2-dimensional motion only. If your motion is in 3 dimensions, this one vectorial equation is 3 dimensions if you analyze the motion in 3 dimensions. Okay? So when you're working with the problems, the first thing to do is you decompose the force into the axis, x and y, and make separately 2 different equations, then work out these equations. An immediate example. It says there is a particle of mass 0.4 kilograms, and there is also a force on this particle. The force is vectorially given as -2 newtons in the x direction and -4 newtons in y direction. So the force is -2i minus 4j. This is the first force acting on the particle. A second force acting on the same particle also is given. It is -2.6 newton in the x direction and 5 newtons in the y direction. It says if the particle is at origin, that means its initial position is 0, right? And it starts from rest, that means its initial velocity is 0. At t is equal to 0, find its position and its velocity at t is equal to 1.6 seconds. So obviously, the problem will help you to find these positions in x and y separately. But since x and y will be calculated separately, what to do is, first, you have to add all the forces on the object, like I am doing now, because Newton's second law says all forces acting on the particle will be equal to its mass times its acceleration vector. But the forces are 2-dimensional, x and y, so I can decompose this. All the forces in the x is equal to m times ax, and all the forces in y is equal to m times ay. This is equal to, since the force 1 has x component -2, and the force 2 has x component -2.6, then the total forces in the x component is -4.6. Right? True? Total forces in the x component is equal to F1x plus F2x. Okay. f1x is given in the problem minus 2, and f2x is given in the problem, it is minus 2.6. You know what these I and J's are, right? I ve C'nin ne olduğunu biliyorsunuz değil mi? Ne? I ne?
Bir tane yönden bahsediyor.
X ne?
Düzden hocam işte.
I, X yönündeki birim vektörü.
Evet.
J de Y yönündeki birim vektörü. Tamam. Niye diye sordu da oradan cevap vermek istedim. Şimdi then the Y component, total of Y components is F1Y plus F2Y. Then you will add the coefficients in front of J's. So F1Y is minus 4 and F2Y is 5. So total forces in the Y direction is 1 Newton. And this is equal to 1. So the rest is very easy. Just solve for AX and it will be minus 4.6 divided by 0.4 because the mass of the object is 0.4. So AY is equal to 1 divided by 0.4. But we are not done yet. And the question says, what is the object's position in X and Y, of course. Well, to find the position vector, it is enough to find its components, Rx and Ry, or X and Y. And how to find X? Remember, this, since what you found is acceleration, and this acceleration vector for the object is constant, right? What is the most general expression for a constant accelerated motion for the position? And you will remember that this is the most general expression for a constant accelerated motion. The initial position in X, the initial velocity in X times t plus 1/2 ax times t squared, of course. So in the problem it is given that initial position is 0 and the initial velocity is 0, so you only left with the acceleration 1/2. Ax is minus 4.6 divided by 0.4, and the problem says define the position at time t is equal to 1.6 seconds, so you will square 1.6. This is the answer for x position, and for y it's the similar 1/2 a, this time a y t squared, and 1/2 1 divided by 0.4 1.6 squared, and this is the y position. And to answer the position vector, what the position vector is, what you do is just add these answers xi plus yj. You find x and y from these equations and write the result as a vector, okay? Because it says, it asks about the position vector. Similarly, what is the most general expression for velocity in the case of constant accelerated motion? And Vx is just V0x times plus Ax times t. This is the most general expression, right? But since V0x is 0 and Ax is again minus 4.6 divided by 0.4. T is 1.6 seconds. This is the x component of the velocity, and the y component is just ay times t, 1 divided by 0.4 times 1.6. And if the problem asks you the velocity vector, then you will write this result as vxi plus vyj. And these are to be calculated from these expressions. That's it. Any questions? So when solving problems, you always decompose everything into x and y, and the rest is just your previous knowledge, x and y, vx and vy, from chapter 2. All right. There is a special state of the objects, which is we call equilibrium situation. We say that the objects are in equilibrium if all the forces acting on the object is equal to 0. For example, this bottle is under gravity, right? The gravitational force is pulling it, but it stays at rest. It is in equilibrium, and all the forces on the bottle must be equal to 0. But there is one force which is down, so the other force must be upward, right? What is this force? This force is the contact force between the bottle and the table. And this contact force is always up. It's always normal to the surface of the table, and it is always up. So this contact force, you can easily say, must be equal to the weight of the bottle, so that this is in equilibrium. Okay? It is not moving. So we will see these normal forces in a while in this chapter. So this is a special case, and if the object is in equilibrium, then its acceleration must be equal to 0, because the forces are equal to 0. So m times a is equal to 0. M cannot be 0 because the object has a mass, non-zero mass. A must be equal to 0. But I can say that for the equilibrium, the object need not stay at rest. The object may move at a constant velocity, because constant velocity has a 0 acceleration, right? The object has 0 acceleration, but it's moving with a constant velocity. If it has a 0 acceleration on the object, then all the forces on the object must be equal to 0, because the force is equal to m times a. If a is equal to 0, then the force must be equal to 0. So this equilibrium situation is also can be true for objects moving at constant velocity. If the object moves at a constant velocity, then you can say all the forces on the object is equal to 0. Well, to analyze the situation separately, what you do is you equate all the sum of the forces on the x and y to 0 to find the forces. Okay. So as I said, the unit of force is 1 newtons, and it is 1 kilogram meter per second square. Before we enter finding the forces acting on the objects, there is a very useful tool which we call the free body diagram. When we are determining the forces on the object, what we do is we draw a diagram. Okay? In the diagram, we usually denote the object as a point, and on this point we show all the forces. Okay? Let's concentrate on an example. If you are holding a book on your hand, okay, and if you hold it without any motion, then obviously you are applying a force on the book, right? If you see everything from the reference of the book, okay, and if you want to draw all the forces on the book, on the right hand side, what you do is you just make a point on the center of the object and show the forces. Okay. First of all, since this is on the surface of Earth, there must be a gravitational force which is downward, right? And we denote this force usually a W. W means weight, and weight is a type of force. We will see how the weight is related to the mass of the object. It is just m times g. In fact, I will explain it. But since the book stays at rest without motion, then there must be another force on the book in the opposite direction to its weight. And in fact, this force is nothing but the force of your hand, okay, applying to the book. It is the contact force by your hand on the book, okay. So this we call a free body diagram of this book, not your hand, only for the book, okay. There might be more than one objects in the picture. If you want to draw the free body diagram for only one, you just think of one object. Free body diagrams are drawn only for one object. You cannot draw free body diagrams at the same time for more than one object. Okay? You cannot draw, for example, free body diagram for two objects at the same time. So this is one of the simple example of a free body diagram. So think about this example. You have a traffic light. It's an object. And it is hanged by these three ropes to the ceiling, some kind of ceiling. And we want to draw a free body diagram. That means if you want to draw a free body diagram, you will show all the forces. That's it. In the free body diagram, you don't show anything else other than forces. Just only concentrate on forces. Okay? But in here, there are two different points that you should draw a free body diagram. One thing is, if you only concentrate on the traffic light, okay? That's the free body diagram for the traffic light in this case, okay? One force is pulling the string which is attached to the traffic light. It is upward, and the other force is downward. The weight of the let's say traffic light, and it is down. So this is the free body diagram for one object and for the traffic light in question. That's it. But there are also other forces that you can see in this picture. One is the force in the left string and the other force in the right string. These are the tension forces. And these tension strings are connected to T3, another string, at one point. If different kinds of forces meet at one point, you also have to draw a free body diagram of this point. Okay? There is such a case in here. So we draw the free body diagram for this point only, separate than the traffic light. You just put a point here, and it's very easy to draw forces because the forces are in the direction of strings. this one T1, we call this is T2, and this part of the string is T3. By the way, when we are talking about the forces on the string, tight strings, we usually label them by T, capital T, okay? T1 is a force. T is force, and it is tension. And by the geometry, you can easily put, first of all, the coordinate system, right, which puts this point onto the origin. This is the horizontal axis. And you can easily determine the angles of these forces with the axis. For example, the angle between T2 and the x-axis is 53 degrees because the string is attached to the sailing with a 53 degrees angle, okay? By the inverse angle theorem that you can easily show in here, these angles are the same, right? From the geometry. Also, these angles are the same. Ters açılar mı deniyor? Ters açı.
İç ters.
İç ters.
Güzel.
So, once you determine the forces, the main thing is to find the components of these forces. And to be able to find the component of the forces, you have to determine the angles. Without finding the angles, you cannot determine the components. And in this picture, you can easily say, since the object stays at rest, both the object and the point, this point and the traffic light stays without any motion. You can easily say that all the forces, sum of all the forces must be equal to 0, because it's in equilibrium position. So you can write the total of tension, or T1 plus T2 plus T3 must be equal to 0. Also, from the first free body diagram, this one, the forces are T3 plus the gravitational force of the object, Fg, must be also equal to 0. Okay. Any questions so far? So the next thing is, after we decompose the forces, after we determine the forces, we decompose them into x and y components. So always, total of forces in the x component and total of forces in the y component, start with this. And for the second case, for this one, which forces have x components? T1, T2, or T3? As you can see, T3 is down, so there is no any projection of T3 onto x-axis. Only T1 and T2 have x components. And these components are, for T2, for T1, it is the magnitude of T1 times cosine 37 degrees, but it's minus because the component is in the negative x direction. On the other hand, T2 component is on the positive x direction, and it is T2 times cosine 53. And when we equate the sum of forces to 0, what we do, we equate sum of all forces in the x direction equal to 0, and the sum of all forces in the y direction equal to 0. Okay? When we equate forces to 0, we have, in fact, two equations. So we have done the first one. From the first one, you can easily find T1 in terms of T2 in terms of T1, right? T2 must be 1.33 times T1. And from the second component, Fy is equal to 0, total forces on the Y is equal to 0, you can also find T3, right? But T3 is given in the problem, right? T3 is nothing but it's the weight of the traffic light, okay? So the T3 can be simply put into the equation, and on the left hand side we have T1 sine 37 degrees, T2 sine 53 degrees, but since we know how to express T2 in terms of T1 from the first equation, the second equation can be made only in terms of T1. So the rest is, you can solve for T1, and once you find T1, you can solve for T2. So this is the example of application of free body diagrams to an object which is in equilibrium. Should we give a break now and then continue? Okay, 10 minutes break. We will continue.
Orasına çıkamadım da bir şeyler atıştırabilir miyim? 5 dakika.
Tamam. So let's look at another example on the application of Newton's second law. We have a boat and 3 men are pushing the boat from the side, as you see. Each man can push the boat with a force of 80.5 newtons, and the mass of the boat is given 753 kilograms. In both cases, in the first case, all of the men are pushing the boat in the same direction, toward right. In the second picture, 2 of the men are this time reverse the direction, and they are pushing the boat in the reverse direction, whereas there is only 1 man pushing the other direction. So we will find the acceleration in both cases. So the problem is easy. What you do is, since these type of problems, you always choose a coordinate system again, okay? So the coordinate system is important, and we usually take this right as x, increasing x direction, and this case all the forces will be in the x direction only. There are no any forces on the y direction. Since all the men are pushing in the same direction, the total of the forces must be the sum of all 3 forces, and they are in the same direction. 3 times 80.5 newtons is the total force, and if you divide it by the mass of the boat, you will find the acceleration toward right, 0.321 meter per second square. In the second case, the force by the man L and C in the negative x direction, so that's why we take these contributions as negative and the other one is positive. If you add these, you will find the resulting force will be in the negative x direction as minus 80.5 newtons, and you divide it by the mass, you will find the acceleration in the second case. In the second case, since the net force is toward the negative axis, the acceleration also will be negative. This example is seems more complicated, but again, it's easy. We have a boat, and the boat is pushed by this propeller, okay, on the back of the boat, and this propeller force is pushing the boat toward right, but there is a frictional force in the reverse direction by the water. Although the water has a very, very small frictional force, but eventually we have this frictional force on the water. It's the force between the boat, the surface of the boat, and the water. But the problem gives the net force, okay? The total of the propeller force and the frictional force is given, and it is given as 7.7 times 10 to the 2 newtons. Okay? So you don't add these two forces because already the addition of these two forces are given. Okay? So just plug and chuck in the A is equal to F divided by M equation. M, the mass of the boat, and the buoy is also given, 3.5 10 to the 2 kilograms. So you find the acceleration. The second part of the problem says, starting from rest, how long does it take the boat to reach a speed of 12 meters per second? Obviously, since you have a constant acceleration, you will use this velocity expression. V is always equal to A times T. And the question is, the velocity is given. The final velocity of the boat is given as 12 meters per second. And since we know the acceleration from the previous part, you can find time it takes to reach this velocity, 12 meters per second. So what you do is just solve V is equal to AT for T and divide V by A to find 5.5 seconds. To 5.5 seconds needed to reach for the boat to reach a 12 meters per second velocity. The third part is interesting. After reaching that speed, the pilot turns off the engine and drifts for a while to stop the boat at a distance of 50 meters. Find the resistance force. This time you will find the frictional force between the boat and the water. Yes? Okay. Okay, we will start here, right? The second part of the problem says the boat reaches a speed of 12 meters per second. But after this, the engine stops, and in that case, the only force acting on the boat and the buoy is the frictional force, because there will be no propelling force anymore if you stop the engine. The only force will be between the water and the boat. The boat, it says, stops at a distance of 50 meters from stopping the engine. By using this information, you know the final velocity, because in the final, the boat will stop. So the final velocity is 0. And you know the initial velocity because the boat had already reached a speed of 12 meters per second. And we know this. There is such an equation, V square is equal to V0 square plus 2 times A times X from our previous chapters, right? If you only know the velocities and the distance, or velocities and the acceleration, you can find the distance, or vice versa. There is no time in here, no any time information in here. So from this formula, you can easily find by putting all the values in here. V0 is 12 meters per second, and distance is given 50 meters, okay? So you can solve for the deceleration of the boat, because after the engine stop, the speed of the boat will decreasing, right? Will be decreasing. There will be a deceleration, or inverse acceleration, or negative acceleration, whatever. But we already know that a force on the object is nothing but its mass times the acceleration, right? From this information only, we can find the value of the frictional force. You multiply this acceleration, it is negative, by the mass of the boat. If you multiply this in the second part here, you will find minus 504 newtons. This force will be the frictional force or the resistance force applied by the water to the boat. Okay? So far we were finding the forces, we were finding the accelerations by using the forces given in the problem. In the last part, we are given the acceleration to find the force. Okay? We are going in the reverse direction. We can always do that. Any questions with this problem? Let's concentrate on another problem. There are two horses, and a load is drawn by these two horses. Horses are pulling the load, but they are pulling in different directions. All right? And these directions are given. The first horse, the horse on top, pulls with an angle of 30 degrees with the x-axis. This is the x. And the second horse is pulling in the direction minus 45 degrees from the x-axis. And the mass of the load is given. It is 2 tons, 2,000 kilograms. And the forces, each force exerts a force of magnitude 600 newtons. Okay. The magnitudes of the forces are given also. And the question is the acceleration. Okay. You might say that, okay, the magnitudes are given, the mass is given, so we are ready to find, but you have to be careful because these are vectors. First of all, you will find the x component of the acceleration by adding the x components of the force. And you will find similarly the y component by only considering the y components of the forces applied by the horses. So let's do the first part. The first part, the x component of the forces will be in the same direction because they are pulling toward the positive x-axis anyway. And the forces are given as 600 newtons. You just multiply these forces by cosine 30 degrees and cosine minus 40 degrees. But cosine of minus angle is cosine of the same angle with the plus, right? Minus or plus doesn't make any difference. The result will be plus. And if you do this multiplication calculation, you will find the x component as 0.472 meter per second square. Is there anything which is not clear to you so far? What we do is just find the x components or x by using the trigonometry. So you will do the same for the y components, but there is a mistake in here. These will be sine. These are not cosine. These are sine. Because when you are finding the y components, you always use sinuses of the angles, from trigonometry. So multiply these magnitudes by sinus 30 degrees and sinus minus 45 degree. You will see that one of the horse will pull in the negative x direction, but the other force will be pulling in the positive y direction. So you will see this from the calculation also. This component will give you a negative contribution. The force which is pulling down has a larger y component. That's why you have at the end minus acceleration in the y direction, minus 0.062 meter per second square. But the problem ask the magnitude of the acceleration. What you find is only the components of the acceleration. To find the magnitudes, you have to take the square of these quantities, add them, and take the square root. Okay? The magnitude is just the square of the components and add them. You will take the square. So you find the magnitude of the acceleration as 0.476 meter per second squared. And you can also find the direction of the acceleration by taking the inverse tangent of the ratio AY divided by AX. And if you find this in your calculator, the calculator will give you a negative angle, minus 7 something, because the acceleration is somewhere down in the x-axis. Okay, it's going in the negative y direction. Nerede? Ha, evet. Onları düzeltirsiniz artık arkadaşlar. Orada bir bu sonucu nasıl etkileyecek? Şunlar 4.7 72. Bu da eksi 0 62 olacak. Nerede 3 yazmışlar?
Soruda 3 yazmışlar.
Ha, bu doğru mu? Ha, burada o zaman onu 10 üzeri 2 yapalım. Okay. I will put these notes into the web page anyway. You can check, but of course it must be correct. All right. Okay, so I think this type of calculations with the second law, finding the components of the forces and using the free body diagrams, etc., is clearer to you now. There are always extra problems, extra examples on your book. You can check them. So we continue with a very special type of force, which is called the gravitational force. And this is the reason that one of the most important reasons that we exist today, as the universe is governed by this gravitational force. The gravitational force says that every object in the universe, if it has a mass, okay, attract each other. Every masses attract each other. Be it atoms, electrons, protons, planets, stars, galaxies, everything attracts each other, okay, in the universe. And this attraction is proportional to the masses of the objects, proportional to the multiplication of the masses. If you increase one of the masses twice, then the force of attraction will be twice, okay? And inversely proportional to the distance between the masses, okay? If the distance between the masses is r, and if you increase this distance by 2, the force between them will be decreasing by 4, because it is inversely related to the square of the distance. So m times m2, m1 times m2 divided by r squared is the gravitational force, but we also include one constant, which is capital G, and it is one of the physical constants of the universe. It is called the gravitational constant in the universe. It is the same constant everywhere in the universe. It is the fixed number, okay? And its unit is given by this crazy m cube kilogram to the power minus 1 and seconds to the power minus 2. And it's a very small number, if you see, 10 to the minus 11. Okay? It's a very small number. That's why you don't feel the gravitational attraction between your punches. Okay? You don't feel, because their masses are not enough to make you feel this force because this constant is very small. But what you feel is that you feel the gravitational force of the Earth. It's not because your mass is large, it's because the mass of the Earth is very large. Okay? Because it depends both on your mass and also on the mass of the second object. In the case of gravitational attraction, your mass and the Earth's mass is, anybody knows what's the mass of the Earth? I don't remember now. You can check. But it's huge. And I know that the mass of Sun, our star, can take 1 million Earth. Okay? It's the mass of 1 million Earth. It's huge. That's why the Earth rotates around the Sun. That's because of this gravitational attraction. This is called the Newton's law of universal gravitation. Everything is pulling. It is this famous story, you remember, Newton's taking a nap under the tree and an apple fall down on his head, and suddenly he finds the laws of attraction, the laws of gravitational attraction. And he notices that this same force, the same kind of force, is pulling also the moon on the orbit of around the Earth. Okay. Another type of force which is important our daily life is the weight. And the weight is, as I said, nothing but the force attracted, the force applied by the Earth on the objects, on the surface of the Earth. And this force is given by the mass of the object the mass of the object times g. Remember this g from previous chapter? It's the gravitational fall acceleration. It's the gravitational acceleration of the Earth. And it's the same g. It's the 9.81 meter per second square. So if you multiply this g by the mass of the object, then you will find the weight of the object on the surface of Earth. And the weight is not universal, as you can see. It's only unique to the surface of Earth. Your weight will be different on the surface of Moon. Your weight is different on Sun. Your weight will be, of course, larger on Sun than on Earth. And it will be less on the Moon than Earth. Because of the g. G is different for different planets. Since weight is a force, it has the same unit with the force. It's Newton. Weight, sometimes you don't feel weight. Can you tell me the case that you don't feel your weight on Earth? What you do in order to not to feel your weight? Ağırlıksız hissetmek için ne yaparsınız? Ya da bir binanın tepesine çıkıp atlarsınız aşağı, değil mi? Siz düşerken hiçbir zaman ağırlık hissetmeyeceksiniz. Çok kısa bir süre için. Paraşütle atlarken ağırlık hisseder misiniz? Ama daha az ağırlık hissedersiniz. Of course, when you first jump from the plane into air, you won't feel your weight. Okay? Of course, when you jump, the duration that you stay on the air, you don't feel your weight. Or when you go outer space, you don't feel weight. So weight is not universal. Weight depends on where you are. Okay. Also, if you go to polar regions, your weight will be larger. Your weight on the North Pole or the South Pole will be larger than here. Why?
Daha yakın.
Nereye yakın?
Ekvatorla kutup arasında devam mı?
Because G is larger on the poles. Okay. well, the shape of Earth, as you said, is not a perfect sphere. It's a little squeezed on the poles. Okay, there is an example, but it's about weight. I'm leaving it to you. It's a simple example. You will just calculate the force applied on a firefighter when it's going down. But there is another interesting place in the elevator. The weights can be different just when the elevator starts its motion and ends up in motion. So at the beginning, when the elevator starts its motion, of course it will have some acceleration, right? It will have acceleration in the upward when it starts going up. Also, when it is slowing down, it will have an acceleration. During these times, you feel a different weight. Why? Suppose you have this situation, okay? You have these two different situations in the elevator, and to show this nicely, a scale. This scale is used to measure the weight of this fish. Okay. First, when the elevator is going up with an acceleration, and this in the second case when the elevator is going down. Before we analyze this, what will you say about these scales? Will the fish be larger in weight when it's going up or down? Its weight will be larger when it's going up or down. Asansör yukarı hızlanırken yalnız. When it's accelerating, not going with a constant velocity. Initially, when it's accelerating, will the weight will be larger or less? Larger. Okay, let's see then. We will calculate it. Before that, let's take the increasing y direction as the upward, okay? So that we can do the calculations correctly. So in the first case, or in any case, doesn't matter. We will work with vectors. Tension, well, if you think this free body diagram, okay, here, the fish. Remember, free body diagrams are drawn only for one object. So let's think about this fish. And all the forces on the fish one is T, right? From now on, the forces which are in the upward direction will be taken as positive. Okay? And the forces which are going downward will be taken as negative. So, since the tension is up and the weight is down, weight is always down, T minus mg, because the total forces, as I said, is equal to mass times acceleration. And we are applying the Newton's second law in here. So the total force is T minus mg, and this will be equal to m times a if the acceleration is up. Because I already set up the direction, the positive direction as upward, and in the first case, acceleration is up, then I take acceleration as positive, okay? So let's check. What is the measure of the weight? It is the value of T, right? The tension. Tension on the rope will give you the weight. Am I right? T is equal to mg plus a. So remember, when the object stays at rest, no motion, the weight is mg. But in here, the tension in the spring or rope is m times g plus a, and a is positive. So when the elevator goes in the up direction, upward, your weight will be larger. Right? So think about the second situation. Again, in the second situation, the forces are, again, T is positive because in the upward direction, and mg is negative. T minus mg. But this time, the A acceleration is downward. So I will take minus mg. Sorry, minus m times A. Right? And if you do this, if you solve for T, because T is a measure of your weight, m times g minus A. So this time the tension in the rope is less because you subtract A from G and you have a less weight. If the elevator goes down initially with an acceleration of G, then T will be 0, right? Because if A is equal to G down, that means your elevator is falling down. Or you just jump off on top of a building. Because you're jumping down, A will be minus G, and G comes from your weight, G minus G is 0. So that means you will feel a 0 weight when you are up in the air. Okay. This apparent weight, that what is called is apparent weight, is just tension on this rope. Okay, apparent weight might be less than your real weight or larger than your weight, depending on the acceleration of the elevator. Okay, so far we have seen 2 laws of motion, but there are in total 3 laws of motion. And we are left with the third law. Third law is about the objects which are in contact, which are touching. Like my cell phone resting on the surface of table, and they are in contact to each other. And my cell phone is motionless, but it has a weight. Then there must be a contact force between my cell phone and the surface of the table. When you're walking on the surface of Earth, again, you are not going towards inside the Earth because there's a contact force between your feet and the floor. When your weight is pulling down, the contact force between you and the surface is pushing you up. These forces are balancing each other so you don't crash into the floor. Okay? So Newton says that whenever there are 2 objects in contact to each other, if one object applies a force on the other object, the same force is applied on the second object by the second object towards the first object. If I am pushing this in this direction, also this is pushing me in the opposite direction. You see, right? I am pushing this, but it is also pushing me in the opposite direction. These forces, the contact forces, are equal in magnitude, but they are opposite in directions. Okay. If you have 2 objects, let me draw you here. They are in contact to each other. Okay. If you're pushing this first object towards the second one, that means there is a force by 1 towards 2. The second object also pushes the first object in the opposite direction by 2, F2 by 1. The force by 2 applied on 1. Okay? You can read like this. And these 2 forces are equal in magnitude, but their directions are opposite. Okay? So this is it, and we will do some examples. This is true for also objects which are pulling or pushing themselves without any mediating, without any touch. If the earth is pulling you towards the center, you are also pulling earth towards you. But you are falling onto earth, not the earth falling onto you. Because it is very hard to move the earth, right? Only by the force between you and earth. The earth can accelerate you with the acceleration of g, right? But why you cannot accelerate earth with the same g? Because the force is just your weight, and your weight is like 70 kilograms or so. This, let's say 70 kilogram, this 70 kilogram can produce an acceleration of the earth, how much? Acceleration is, let's say 70 kilogram, the force, divided by the mass of the earth. And the mass of the earth is very, very large. If this is very large, and A is close to value to 0. In fact, you are also pulling the earth toward you with some acceleration, but this is very, very, very slow. Okay? So why this is, we say, why the earth does not fall onto you, but you fall onto earth. Okay, this may be a confusing to you, but if you think more, then you can find the answer. So I'm skipping this. It's a very trivial question. You will find the acceleration of a woman and a man. Well, these action-reaction pairs are very important to move your car. Arabanız nasıl ilerliyor? Well, the engine is pushing your, we know that the engine is pushing your car, but what the engine does is just to rotate the wheels of the car, that's it. In fact, the frictional force between the tire of your wheels, between the tire of the car and the surface of earth is pushing your car. Okay? Because when the tires are touching on the surface of the floor, the tires are not skidding. Skidding is patinaj. Patinaj yaptığı zaman hareket etmez değil mi araba? Çünkü arada sürtünme kuvveti yok olur. Okay. So let's do some questions, some problems. There is an interesting question. Suppose you have these two boxes, okay? And in the first scenario, in the first case, you push the second object with a force towards the first object, okay? And in the second case, you push the first object towards the second object. When you push the second object towards the first object, what is the force on the first object? Is it F? Question. Suppose there is no friction on the surface, okay? There is no friction. You push the second object with a force F, and of course the first object will feel a force on it. But this force, let's call this force F, the force on 1 by 2, okay? My writing is very bad. The force on 1 applied by 2. Is this equal to F? the same question I'm asking here also. When you push the first object towards 2, the force on the second object is it equal to F? Yes or no? Who says yes? Who says no? Who says no? You? One? Only one? Two? Three? And yes diyenler 2 mi? 3 mü? Gerisi bir şey demiyor mu? Ha? Kararsız olmayacaksınız. Either yes or no. Who says yes? Okay, half of the class says yes. Okay, tamam. 50-50. So let's analyze them. Okay? Yarınız aynı kuvvet diyor, yarınız değil diyor. Let's see. Okay, let's take a numerical example. Okay? Now I am pushing the 3 kilogram object by a force of 3 newtons toward left, and 1 kilogram object by a force towards right. And the question is the net force on the larger block, on this one, less than 2, equal to 2, or larger than 2? People who say yes in the previous case must say 2 newtons, right? There is no friction. There is no friction. The force on the larger object is less than 2. Who says that? Who says it is equal to 2? Who says larger than 2? Okay. Neden daha düşük?
Bende 4 kilogramda net kuvveti 1 bölü 2'lik bir ivmesi var. 1 bölü 1,5.
Okay. So as your friend suggests that let's apply the Newton's second law first. Okay? First of all, what is the net force on the whole system? 2. Good. Towards right. Right? And with this information, you can find the acceleration of each block, right? Will the acceleration of each block be the same or different? Who says different? They move together, okay? So they move together, so they will have the same acceleration. Let's find this acceleration first. The total force is 2, right? Let me write it in more compact notation. The total force is equal to the total mass, this mt is total mass, times the acceleration of the whole body. So the acceleration is, the total force is 5 minus 3, because we are taking the positive acceleration as the positive, divided by the total mass is 4, and it is 1/2. Okay. So each block has acceleration of 0.5 meter per second. Good. If this guy is moving an acceleration of 1/2, then I can find the force applied by the first mass, 1 kilogram, onto the 3 kilograms, right? Let's call this force as F 1,3, okay? And according to the Newton's law, the total forces on 3 kilograms body must be equal to its mass times acceleration, right? And I don't know F13 yet. So the question is, find F13. Is it larger than 2, equal to 2, or less than 2? F13 minus, because F13 is in the positive acceleration, right? Minus 3, because there is another force on 3 kilograms. 3, and this is equal to its mass, 3 times 1/2. All right? So from here, F13 is equal to 3 plus 3/2. 3 plus 3/2 is 4.5 kilograms. But the question is, what is the net force? What is the net force on the larger block? So the net force on it is obviously this is not kilogram. This is newtons. 4.5 net force on 3, it is 4.5 minus 3, because 3 is in the negative x direction. So it is 1.5. And it is less than 2 newtons. Any questions? What can you say about the net force on the smaller block? Is it larger than 2? Bir kilogramlık kütle üzerinde. To find the net force on acting on the 1 kilogram body, what other force must be taken into account on F1? There is one force which is 5 newtons, okay? And what is the other force on F1, on the first block? It is according to the Newton's third law. The contact force on 1 kilogram body must be the same with F13, but it will be in the opposite direction. So the contact force on the first body, 1 kilogram body, is, let's say, F31, and the net force on the first body, that F1, is 5 minus 4.5. See, we take minus sign in here. In here, F13 is plus 4.5 because it's going to work. Because of the action-reaction pairs, in the second case, F31 must be in the opposite direction. So in that case, F1, the total net force on the 1 kilogram body is equal to 0.5 kilograms. It's again less than 2 newtons. Alright, I think this is understood. You will have a more complicated problem in one of your quizzes, next quizzes. You will have 3 bodies, okay? In addition, block, or maybe even more, to calculate the forces between the blocks. There is another type of force which we call tensional force on the ropes. Okay, this force sometimes might be harder for you to determine, but there is one rule at every point. At every point, the tension force is the same. Okay, if you are pulling a rope from this end if you are pulling rope from this end with a tension T, then the same tension happens on the other side but in the opposite direction. Okay? A question for you. Suppose you are pulling, you are holding this pulley, okay, this pulley with a tension T in your hand, okay, so that the object stays at rest. This one stays at rest, balanced in its initial position. What is the weight? What is the weight of this object in terms of tension T? One rule about the ropes, tension.
20.
On the same rope, on the same string, tension is the same. Okay? So if this rope is the same with this part, this is the same thing, and this part is also the same rope, this part is also the same rope, because they are all connected, they are all the same rope. This tension, and this one are all the same. So 4 tensions are up and the weight is down, so the weight must be equal to 4T. Or T on the rope is equal to the weight of the object divided by 4. So again, you will need this information when solving problems, including the ropes and tensions. And last thing, okay, last type of force in this chapter is the normal force. Whenever you put an object onto a surface, which is a rigid surface, the object stays at rest even though it has a gravitational force acting on down. So in order to those objects stays at rest, there must be another force which is in the opposite direction to its weight. If you put an object on the surface like this, okay, first of all, if you think it's free body diagram, in the free body diagram there is only one force pulling it down. But since it stays at rest, there must be another force on the same object which is in the opposite direction, and this force must balance its weight. Okay? The normal force on the surfaces, on any rigid surface, is always normal to the surface. What does that mean? The normal force being normal to the surface means the force, if this is the surface, has a right angle. If this is the surface, and this must be the direction of the normal force, because it has always a right angle with the surface. Okay? Normal kuvveti her yüzeyde her zaman yüzeye diktir. Eğer yüzeyiniz eğrildiyse normal kuvveti onunla beraber eğrilecek. Eğik düzlemde normal kuvveti şöyle olacak. Düz yatay düzlemde böyle. Böyle, sürekli böyle. Sürekli yüzeye dik. Okay. So this is the only rule about the normal force, and the normal force is always away from the surface. Okay? Not into the surface, it must be away from the surface, especially it must balance the weight of the objects on the surface. So you can determine its direction easily. But if there are external forces on the object, suppose you have this suitcase on the floor, and of course there will be weight of the suitcase down. Again, it's normal to the surface, it's perpendicular to the surface. And the normal force is up, But if we apply an external force, like a force in this direction, then the normal force will have a different value. It will be less in this particular example. Okay? Because there is a force, and some component of this force is pulling the object upward. If something is pulling the object, but still if the object is on touch with the surface, then in that case the normal force will be less than the weight of the object. But if there are no external forces, in this case the normal force will be equal to the weight. But if there are external forces, the normal force will be different than the weight of the object. For example, in here, let's think the normal force, calculate the normal force in here. The normal force in the first case, this one, will be equal to, sorry, not weight. The normal force will be equal to weight minus F times sine theta. This is the angle. Angle is between the force and the horizontal direction. Because this force has a component in the vertical direction. This is the vertical direction. As a vertical direction, Fy, and this Fy is nothing but F times sine theta. But this Fy is in opposite direction to the weight, so the normal force will be calculated by subtracting this force from the weight. Okay. In this case, the normal force will be less than the weight. But in other cases, for example, in here, these two boys are pushing this box. Is pushing this box down. Not exactly down, but some angles, okay? They're applying forces. These forces has components which is downward, okay? In that case, the normal force will be larger than the weight of the box itself. Because we can calculate this, I think here. The force applied by the first boy, F1, has a component downward in the y direction, minus F1 sine 60 degrees. If you take the y direction as the upward direction. Similarly, the second boy applies a force which has a negative component in the y direction, F2 minus F2 sine 30 degrees. And we have numerical examples. The magnitude of F1 is 13 newtons. The magnitude of F2 is 11 newtons. And the problem is, what is the acceleration of ice? Well, don't think about this example, but let me calculate the normal force, N. If the box stays at rest, the total forces, remember the equilibrium? If something stays at rest, its acceleration is 0. That means the total forces acting on the object must be equal to 0, right? But to find the normal force in this picture, it is enough to calculate all forces acting on the y direction only, because normal force is only in the y direction. So let's calculate all forces in y only. And this will be equal to 0, right? Because it's not moving. With this choice of coordinate system, the weight is negative, right? And F1 has a downward component in the y direction. It will be also minus F1 times sine 60 degrees Also, F2 is down minus F2, but it has a different angle, sine 30 degrees. And there is one more force, which is the normal force, which is upward, so it must be plus, right? And all this must be equal to 0. So you can find the normal force in terms of the weight. The normal force, if we solve, weight plus F1 sine 60 plus F2 sine 30 degrees. Since F1, F2 are positive, they are the magnitudes of the forces, and sine 60 and sine 30 are positive quantities. As you see, the normal force in this case will be larger than W, the weight, okay? Because weight plus some other positive quantities. All right. So let's finish for today and here. And you have your lab at 3 o'clock, all groups all together, C1 and C2. Çizim yapalım. Okay. A şehrinde. Şurası A olsun. B neymiş? In the direction of 30 degrees. You west from city A to city B. İlk önce ne diyor? 200 kilometre.
200 batıya gidiyormuş.
Pardon, 200 kilometre batıya gidiyor. Tamam.
30 derece yapıp Northwest.
Burada B varmış, öyle mi?
Evet.
Tamam. Şunu çizelim bir. Burası north, burası east.
East, west.
West. Tamam. O zaman 300 kilometrede in the direction of 30 degrees north of west. Buradan da west'in north'u, yani şöyle gidiyor.
Evet.
Ama burası 30 derece olacak. 30 degree north of, evet, daha doğru. Evet. Burası 300 metre olacak. Tamam. In a straight line, bunu soruyor. Evet, in a straight line. How far the sea? Burası C. Burası C. Şu ikisini topluyorsun. Şu.